Alright, so let's do section 2, a brief history of the universe. For those of you in the stars and universe class, we're going to go through this in a lot more detail. This is going to be just a really brief introduction. Right? So we have several pieces of evidence that point to that the universe used to be much smaller, which also means it would be denser and hotter. Now we can't actually see the Big Bang. We can't see that far away. We can't see to time of zero. We have no evidence of time of zero. But the evidence leads us to believe that this is the simplest way to explain way back to the beginning of the universe, when we can see that it was hotter and denser and smaller. And current data puts the Big Bang at 13.82 billion years ago. 13.82 billion years ago. That's actually amazingly precise. Like here on the screen I have it rounded to 14 for you, but we actually have its date much better. We define it as the event that created the universe. So you could say it created all the energy. Energy can turn into mass. It created time and space, if you want to go that far. And from the Big Bang, the only elements that were actually created was hydrogen and helium. There was no oxygen, there was no iron, there was no calcium. Only hydrogen and helium were made from the Big Bang itself. Everything else was later processed in stars. Okay. So that's going to be our time of zero. We'll just call it the Big Bang. Hydrogen and helium, 14 billion years ago. Let's go up in time to the first galaxies. So all we've got is hydrogen and helium gas floating around out in space, and the universe is going to expand and cool. We'll talk about that again in a few minutes here. But the hydrogen and helium gas will cool enough that gravity can start to bunch it up. Gravity is going to start bunching it up and pulling it together into blobs. And the way the laws of physics work is as something's collapsing and getting smaller and denser, it will usually heat up. But also as you go from a blob of gas and it collapses, it will also start to spin faster. That's called conservation of angular momentum. We'll do that in probably chapter 3 or 4. Right? So you're going to actually start making the first galaxies. The hydrogen and helium gas will make your first galaxies, and inside your galaxies your first stars will start to form. Okay? So they're just pure hydrogen and helium. So I like to imagine these first galaxies as having no Earth-like planets. There's no iron to make a core. There's no silicon or carbon to make rocks or dirt. It's just hydrogen and helium. Okay. A star makes its power through nuclear fusion, and that changes one element into a heavier one. So stars will take hydrogen and turn it into helium, and then they can take helium and turn it into something even heavier, a heavier element. So stars are actually what make the carbon in the universe. Stars make the iron. Stars make all of these elements. And when stars die, they make even heavier elements and they explode them back out into the galaxy to be used again. They kind of litter their creation, all their new elements that they made, back into space. So we kind of call that recycling of materials, stellar recycling, gas recycling, element recycling. Okay. So now that you're done with the first stars, you can have carbon and iron. You can actually make a new solar system, and a new solar system now might be able to have an Earth-like planet. Based on kind of estimates, our solar system is a third generation star, a third generation solar system. So 2 other generations have already existed. The stars have died, exploded, given their elements back to the galaxy. And so our planet did form with some of the heavier elements like iron and carbon. So we can have an Earth-like planet. Our solar system is 4.6 billion years old. We have dated meteorites to 4.55 billion years old, and those took some time to form, so we'll say 4.6 billion years ago is when our solar system started to form. And it looks kind of a lot like you're forming a galaxy. You have a blob of gas, only this time this blob of gas will have some carbon in it, some little bits of iron. It'll collapse. Gravity will collapse it, heat it up. It'll also start to spin and flatten, and you can make a solar system. And that is our very brief introduction to history of the universe. Right. Very brief. Section 3 is just kind of a brief overview of how you're moving through the universe. We'll start with local. You are riding on the planet Earth. And the planet Earth rotates once per day. It turns on its axis once per day. And because we live in Minnesota, well, it's an online class, I'll presume you're in Minnesota, you go around a certain size circle every day. And that would lead us to move about 600 miles per hour. Just sitting still, just studying, just reading, you're moving 600 miles per hour. If you're along the equator, you have to travel a bigger circle in 24 hours, so you move faster. But we move about 600 miles per hour just sitting here. If we go to a slightly larger scale, we could look at how the Earth moves around the sun. When the Earth moves around the sun, you can say it's orbiting. The Earth orbits the sun. Or you can say it's revolving. The Earth revolves around the sun. Just be careful with the rotating and the revolving. People tend to mix those up. Okay. Just by Earth moving around the sun, you're moving 600,000 miles per hour through space. That's incredible, and you can't feel it. Your human body cannot sense it. It feels like you're sitting still. 600,000 miles per hour. If you look at this diagram, you can also start to see a few things that we're going to need in Chapter 2. Earth's axis and the ecliptic plane. Right, the ecliptic plane here is defined as this flat blue plane that is defined by Earth's orbit. So our planet, our orbit defined this plane, and we measure from it. We say, oh, it's on the ecliptic plane, or it's 10 degrees above the ecliptic plane. All right, it's just a starting point for measuring. Right. So it's the flat plane of Earth's orbit. The sun is also on the ecliptic plane. Earth's axis is the imaginary line that Earth rotates around. It runs from the North Pole. Here, let me point at the North Pole and the South Pole. And if you follow that line to the north, it would point at the North Star. And the North Star is Polaris in the Little Dipper. Notice that here, let's call this maybe January. In January, the axis is pointed towards Polaris. But if you come back 6 months later in July, the axis is still pointed towards Polaris. The North Star is our North Star, and it doesn't matter which season you're in. Right. Zoom out a little bit further. Earth goes around the sun, and the sun goes around the galaxy. It takes us with it, so Earth is also going around the galaxy. Again, it's not another motion that we can feel. The galaxy, remember, is absolutely huge. Absolutely huge. It would take our sun 230 million years to go around the galaxy once, for one orbit of the galaxy. 230 million years. So it's not something that we humans will notice. We only live 80 years. We don't notice that motion. But it's another 500,000 miles per hour that we are moving through the universe. All the galaxies in space are moving, just everything's always moving. It's hard to keep track of, it makes our job difficult. But we live in the Milky Way galaxy, and we actually have galaxies that are orbiting us. We actually have a couple galaxies that we are also ripping apart, and kind of our galaxy is eating them. The Milky Way is eating a galaxy called the Canis Major Dwarf galaxy, and it's also eating a galaxy called the Sagittarius Dwarf galaxy. We have two galaxies that orbit us. That's these right here, the Magellanic Clouds, the Small Magellanic Cloud, the Large Magellanic Cloud. They orbit our galaxy. The Milky Way galaxy is one of the big ones in our local group, in our neighborhood, but the other big player, and it's probably a bit bigger than us, just a little bit bigger than us, is the Andromeda galaxy. So we are the two big, massive galaxies, and the gravity is pulling them together. So we are actually falling towards Andromeda, and Andromeda is actually falling towards us. And we can add that speed, another 180,000 miles per hour, to how fast we're moving through the universe. Yes, the Milky Way and Andromeda will collide. It is going to happen probably, 2 billion years in the future. Not something you worry about. The last motion that we're going to talk about briefly as kind of an introduction is the expansion of the universe. Now, the expansion of the universe is not something that makes sense. It just is. We've seen it, we've measured it. We haven't really explained it yet. We've got ideas, we've got some hypotheses, but it just doesn't make sense. On a gut level, it just, to a human, doesn't feel right. We're just going to accept that and move on. It just is. Okay. Edwin Hubble in the 1920s was measuring the speeds of galaxies. And there are no distant galaxies that are moving towards us. None of them. Like Andromeda is moving towards us because of our gravity. It's nearby. We're close enough to pull on each other. But all of the distant galaxies, there's something else driving them away from us, driving all galaxies away from each other. And we can talk about that in the universe class a bit more. But basically, the distances between the galaxies are getting bigger. The galaxies themselves are not inflating, they're not getting really bigger, gravity's holding them as tight little knots, but the empty space between the galaxies is getting bigger. So that's universal expansion. All distant galaxies are moving away from us. We have not found any, not one of the thousands we've looked at, we have not found a single distant galaxy moving towards us, which is not something we predicted. This surprised us in the 1920s.